Okay, welcome back. So today we're going to be first going over the homework, and then we will jump to the next section, which is going to be even and odd functions. I think you're going to like this one a lot. So let's go ahead and start off with the homework and take care of that. So we started off, we had piecewise functions that we needed to graph. So the first one was f of x is equal to 3 when x is less than or equal to 0, and 1 when x is greater than 0. Okay, so I'm going to graph this out. Let's see, 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. Alrighty, so what I do at the very beginning is instead of f of x equals this, I can put a little y equals, because that's really what the f of x is. It's synonymous with the y. So I'm going to put a little y equals 3 and y equals 1. Alrighty, so for the first one, I've got y equals 3, and we know that that is a horizontal line where every single value is y equals 3. Makes sense. And then once I get it graphed, I look at the domain, where this thing lives. So this thing lives every value of x that is less than or equal to 0. So everything this direction, because remember the little less than sign is pointing in that direction, of x equals 0. So here's x equals 0 right there, and then it's going to be everything over here. And that means that everything that's greater than 0 doesn't exist for this function. So I can erase that. Alrighty, and now I'll move to the next one. Now that I've graphed that and restricted the domain, move down to the next one. I have y equals 1. And so y equals 1 is going to be a line, horizontal line at y equals 1. And its domain is all the values of x that are greater than 0, but not equal to. So I know that it's going to be everything to this direction of x equals 0. So it's going to be all of these values, but none of these values. So I'm going to erase everything to the left of that. And since I have a greater than and not a greater than or equal to, it does not include the value 0, so I put an open circle right there. And so there you have it. That's exactly what the function looks like when we graph it piecewise. Okay, and so I'm going to move to the next one now. Let me go ahead and clear the screen. And the next one, number 2, was f of x is equal to, we're going to have x plus 1 when x is less than or equal to 1, and negative x plus 1 when x is greater than 1. Okay, so again, I'm going to make my nice graph here. 1, 2, 3, 1, 2, 3. I think I said I wasn't going to do this, but breaking the habit is rather difficult to not count. Alrighty, so let's graph this first one. Well, before we do that, we're going to put our little y equals and y equals. And now this is in the nice form y equals mx plus b, where m is our slope. I don't know if I could have written slope worse if I tried. Let me try that one more time. Redo. Slope. And then b is where it hits the y-axis, which we call the y-intercept. Okay? So the first one, I'll look and see where it hits the y-axis first, and that hits at positive 1. So I'll put a dot right there. And then I'll look at the slope to see where I put the next dot. And the slope that's in front of this x is a positive 1. And the positive 1 is 1 over 1. So I'm going to be going up 1 over 1 for the next point. And then I just connect the dots. Okay. So now that I have it graphed, I can restrict the domain. Where does this thing live? Well, it lives for all x values that are less than and equal to 1, or less than or equal to 1. So this is x equals 1, and it's all the values that are pointing this way from there. So I've got all of these values in this direction. But I don't have anything that's to the right. So I erase that portion right there. And I'm going to, since it includes the actual x equals 1 value, I'm going to put a nice solid dot there. Okay? Now I've finished with the first function. Now I move down to the next one. The next one is y equals negative x plus 1. All right, well, it hits the y-axis at 1 as well. So that's my first dot. And in the next dot, this is a negative 1 in front of here, and that is a negative 1 over 1. And since it's negative, instead of going up, I go down. So it's going to be down 1 over 1 for the next point. And then I just have to connect the dots and assume I can actually connect the dots. Alrighty. So this one is all the values of x that are greater than x equals 1. So this direction from x equals 1, so all of these values right here, and nothing less than x equals 1. So I'm going to erase all of this. I'm going to try to be a little bit careful, so I'm going to erase that now. Since it doesn't include x equals 1, I want to put an open circle right there. And there we have it. That's what the function looks like. And notice there's no overlap at x equals 1 because only the top one includes that point. The bottom function does not. Okay? Now, let's move to the very next, the last of the homework. So, I'm going to erase this. And let's see, for number 3 we had f of x equals, alrighty, now I'm going to have 3 functions. Since I've got 3, I'm going to go ahead and color code them. So, the first function is going to be negative 1/2 x plus 1. And this is going to be for all values of x that are less than or equal to negative 2. And then the next function is 2 for all values of x that are between negative 2 and positive 1. And then the final function, I'm going to have x minus 2 for all values of x that are greater than 1. Okay? So I'm going to go down here and take this, make a nice big graph that I can use. Try to spread this out a little bit. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Something like that. Okay. So now I'm going to move for the very first function, and before I do that, I want to put the little y equals and y equals and y equals. Okay, so I'll go to my first one, and I've got y equals 1/2 x plus 1. Alrighty, so let me reduce my brush size, which for some reason jumped up quite a bit. So I've got my y equals mx plus b format. Y, what on earth is this doing? I'm on the wrong, that's why it was looking strange. I was on the wrong function. Hold on, let me erase this. There we go. So, I start off, I've got y is equal to negative 1/2 x plus 1. The plus 1 indicates that I'm going to have a dot at y. Why is this not working right? Ugh. Forgive me, I am having technical difficulties apparently with this. So at y equals positive 1, I've got a dot there. And then for the next point, I've got the slope is negative 1/2, so that's going to be down 1 over 2. So that'll be the next dot right there. And then I just connect the dots. So here we go. All right. Now that I have the actual line graph, I can restrict the domain. Where does this thing live? Well, it lives all values that are less than or equal to negative 2. So to the left of negative 2, x equals negative 2, it's right here. So I'm going to put the dot there, and it's all of these values that that the function lives under. All the other values I can erase. So all the stuff to the right I can erase. So let's see. Trying to get a thinner eraser where I don't knock as much out. Now, you know what? I don't think that's working. Let me go back to something that's a little bit bigger. Okay. There we go. So now I've got to redraw my graph so I don't have gaps. There we go. That's the first piece graphed up. And now I move down to the next piece. And that one is at y equals 2. So y equals 2 is going to be a horizontal line that is at y equals 2. Okay? And where does it live? Well, the domain of this function is between negative 2 and positive 1. X equals negative 2, x equals positive 1. So it's going to live right between negative 2 and negative 1. X equals negative 2, x equals positive 1. So it doesn't live anywhere else, so I can erase all that. All this. Oh no, I'm going to have to redraw that. That's okay. Now, I need to take care of the endpoints. This doesn't include negative 2, so there needs to be an open circle right here. So let me go ahead and draw that. But on the x equals 1 side, it does include x equals 1. X can be equal to that, so it's a nice closed circle there. Alrighty? And so let me connect that dot, get the graph where it looks like it's actually continuous. Alright, so that's the first function and the second function that I graphed. Now move down to the next one. The next one, we have y is equal to x minus 2. So where does this hit the y-axis? It hits it at negative 2. And then what does the slope look like? Well, the slope is positive 1, so it's going to go up 1 and over 1. And then I'm just going to connect the dots, like so. And now where does this thing live? Well, the domain for this function is all the values that are greater than 1. So all the values of x that are greater than 1 are to the right of x equals 1. Well, right here is x equals 1, so it's going to be all of these values right here. And none of the others, so I'm going to erase all the others, like so. And let me redo that so it's not quite so bad looking. And now, it does not include x equals 1, so I can't include this point, which means I have to put an open circle right there. And there we have it. This is our piecewise function graph. I have first function, negative 1/2 x plus 1, which is all the values of x that are less than or equal to negative 2, so it's that way. Next function, y equals 2, between x equals negative 2, x equals 1. And then finally, the last function, x minus 2, for all values of x that are greater than x equals 1. So to the right of that. And there you have it. That is the final piecewise function for the homework. So hopefully that went well. I'm going to clear and we will start on even and odd functions. So I will see you in a sec. Let's see, clear that. Okay, so this is going to be even and odd functions. And so let's get going. We're going to start with a little bit of a review, kind of set the stage, and I'm going to ask a question. Let's say that I have the equation y equals x plus 2. And I want to know, bear with me, what value do I get when I plug in x equals 1? Okay, well, I'm going to get y equals 1 plus 2, 3. Okay, now what value do I get when I plug in x equals 2? Well, y equals 2 plus 2, I get 4. Now, this is a lot of writing to get an answer out of it. And this is an extremely common thing that you want to do with an equation. You want to be able to plug different values in for your x. And instead of writing all this out every single time that you want to plug values in and get an answer out, mathematicians came up with a shorthand notation, which is the F notation. So F notation to the rescue, because now I can say f of x is equal to x plus 2, and then all I have to do is put the following. I can say f of 1 equals, and this automatically is saying in this expression over here, if I put a 1 in for the x, I then substitute that 1 in for the x in an actual expression. So f of x is x plus 2, f of 1 is 1 plus 2, and I get 3 out. And similarly, if I do f of 2 is going to be 2 plus 2, which is 4. So the F notation is a much easier way to talk about plugging values in for your x. And this is really where the whole synonymous thing comes in with the y and the f of x. They're really talking about the same thing. So y is a function of x, but using the f of x notation lets us plug in values very quickly and easily. And in addition, that f tells us automatically that this is a function. So that's just nice. I kind of like that f does all that for us. So with that in mind, let me clear the screen and we will move to the next thing. So the next thing we're going to do is practice the f notation. Let's say I have f of x is equal to x plus 5. Okay? What would I get if I wanted to do f of 1? Well, f of x is x plus 5. F of 1 is 1 plus 5. So I get 6. What about f of 4? Well, f of 4 would be 4 plus 5, which would give me 9. What about f of negative 3? Well, again, f of x is x plus 5, so f of negative 3 is negative 3 plus 5, which is going to give me positive 2. Now, what about f of smiley face? What would that give me? Well, all I do is I substitute it in wherever there's an x in the expression. So f of x is x plus 5, so f of smiley face would be smiley face plus 5. And you know it's coming. What would I get if I did f of cat? Well, that would be cat plus 5. Okay? So that's how the f notation works. When I have my f notation up here, f of x is equal, when I put a value in for x, I just substitute that value in for every x that's in the expression over on the right, and then I solve. And that's all there is to it. Okay? So let's take that and try something a little bit interesting. Let me clear this. And now let's look at f of x equals x squared. Okay? So it's going to seem kind of redundant, but bear with me. There's a reason why we're going to be doing this. So f of x is x squared. What about f of 1? Well, that would be 1 squared, which is 1. F of 2 would be 2 squared, which is 4. F of 3 would be 3 squared, which is 9. And f of 4 would be 4 squared, which is 16. Okay? Now what happens if I do f of negative 1? What would I get? Well, I'm substituting the negative 1 in for the x, and I'm squaring the whole thing. So I need to put that negative 1 in parentheses before I square it, because it is squaring the negative as well as the 1. So negative 1 squared is negative 1 times negative 1, which is positive 1. What about f of negative 2? That would be negative 2 squared, quantity squared, which is positive 4. F of negative 3 would be negative 3 squared. Negative 3 times negative 3, positive 9. And finally, f of negative 4. That would be negative 4 squared, which is 16. Alrighty. So, notice anything interesting between plugging in positive 1 and negative 1? Yep, they had the same values. Same thing for positive 2, negative 2, positive 3, negative 3, and positive 4, negative 4. Okay, so what it looks like is I get the same result regardless of the sign. And so it doesn't matter if I plug a negative value in or a positive value, I'm still going to get the same result. Now, another way I can put that is, here we go, drum roll. If I plug in a negative x, I get the exact same answer as plugging in a positive x. This right here is the definition of an even function. So this is the definition of an even function. That if I plug a negative value in, I get the same exact answer as if I plugged a positive value in. So this is my definition for an even function. Okay? That really wouldn't seem to be all that useful, but we're going to develop it quite a bit to where it actually means something. So, and if take and pause, think about it for just a second. It doesn't matter if I plug a negative value in or a positive value, I get the exact same answer back and forth. So that means if that happens, that function is an even function. Okay? And that's even. Alrighty. Now, let me go a little bit further into this. I'm going to clear the screen. And now I'm going to do f of x equals x to the 4th. Okay? So what about if I do f of 1? Well, that would be 1 to the 4th, which is 1 times 1 times 1 times 1, which is just 1. What about if I plug 2 in? Well, That's 2 to the 4th, which is 2 times 2 times 2 times 2, which is 16. Okay? Now, what happens if I plug a negative 1 in to f of negative 1? Well, that would be negative 1 quantity to the 4th, which is going to be negative 1 times negative 1 times negative 1 times negative 1. Negative 1 times negative 1, positive 1, times negative 1, negative 1, times negative 1 again, positive 1. So I'll get positive 1. What about negative 2? Well, it's going to be negative 2 quantity to the 4th power, which is negative 2 times negative 2 times negative 2 times negative 2. Negative 2 times negative 2, positive 4, times negative 2, negative 8, times negative 2, positive 16. And there you go again. Again, we get the exact same values, whether it's positive or negative. Okay, so the question then is, this worked for f of x is equal to x squared, and f of x is equal to x to the 4th. Now, in both of these cases, it didn't matter what sign that I plugged in, I got the same value out, whether it was positive or negative. And we said that that is the definition of an even function. Now, it's not a huge mystery, but what do these two expressions have in common that might lead to them being called an even function? And yeah, that's exactly what they have in common. They have even exponents for the variable x. So an even function, when we're talking about single terms like this, are x values that have an even exponent. 2, 4, and if I did x to the 6th, it would also be even, x to the 8th, x to the 10th, you name it. As long as the exponent is even, it's going to be an even function, and it will have the property that it doesn't matter if I plug in a negative value or a positive value, I'm going to get the same answer. Okay? Now, let's move to graphing these and see what kind of strange behavior even functions have. Let me clear this and move to Desmos. Okay, so here we are in Desmos. Desmos.com, if you haven't been here, is an amazing resource for graphing. So we're going to start off, we're going to graph x squared. Okay, so that's what x squared looks like. We've seen that before. It's just a nice parabola. And let me then move down and do x to the 4th. Okay, it's still kind of a parabola, but it's kind of squat down at the bottom. X to the 6th. Well, same thing. It's just a parabola that's kind of squatter at the bottom, if that's such a word. And if I go on out x to the 12th even, you can see it's even more squat down at the bottom. Now, if I graph all of them at once, do you notice, is there anything odd about the graphs? And yes, there's something very, very odd about the graphs. All of the graphs are symmetrical. They are mirrored across the y-axis. It's like a mirror is right here on the y-axis, and it's reflecting the graph. All even functions are symmetrical. They are mirrored across the y-axis. That is one of the characteristics of an even function. And that makes sense because the y values that you get are the same whether it's a positive x or a negative x. So that's why you have the symmetry across the y-axis. Okay? Now, here's a crazy question. Let me turn all these off. What if I did maybe 3x squared? Put a 3 in front of the x squared. 3 is an odd number. Will it affect the symmetry? And the answer, no. It does not affect the symmetry. It's still like there's a mirror right on the y-axis. Okay? What about 7x to the 4th? Nope, that doesn't do a thing. And maybe negative 5x to the 6th. Nope, it is still symmetrical. So, what is this telling me? Well, this tells me that it doesn't matter what the coefficient, the number in front of my variable is, that doesn't affect the symmetry. What's important is that the exponent has to be even. If the exponent is even, you're going to have symmetry across the y-axis. It is going to be an even function. Okay? So now that we have proved that to ourselves, let me turn these off. And let me ask you about a function that we're very familiar with, that we've used a lot, and that is y equals 2. Is that symmetrical across the y-axis? Is it a mirror image? Yeah, sure is. If I put a mirror right here on the y-axis, it's going to reflect this function perfectly back and forth. What about y equals -1? Yep. These are horizontal lines, and so they definitely have mirror symmetry across the y-axis. But does that hold for the same equation, I guess, properties that we talked about before? Because we said before that in order to have symmetry across the y-axis, you needed to be an even function. And an even function has the exponent of the variable even. Okay? Well, it turns out that still holds for these standard ones. And so these y equals 2 and y equals -1. So let's go back to our blackboard and draw that. Okay, so here we are back at the blackboard, and I'm going to put y equals 2. Now it looked like it had the same kind of symmetry as y equals x squared and y equals x to the 4th. And we said that in order to have that symmetry, you need to have an even exponent for the variable, but there's no variable here. Well, actually there is a variable hanging out after 2, it's just hidden. So we've got, first let me refresh just a second, I'm going to say y equals 2. So what is, this seems like a completely out of left field kind of question, but what is the value of anything raised to the 0 power? Well, we studied that a long time ago, and that is, if I had like 5 to the 0 power, what is that equal to? It's equal to 1, right? Doesn't matter what is raised to the 0 power. I could have smiley face raised to the 0 power, and it's still going to equal 1. Anything raised to the 0 power is equal to 1. That includes x. So x to the 0 is equal to 1. Okay, so y equals 2. Well, y equals 2 is the same thing as y equals 2 times 1. And we already said that 1 is the same as x to the 0 power. So this is really y equals 2 times x to the 0 power. So even though it doesn't look like there's a variable here, there is a variable here. It's just raised to the 0 power. Okay, and is 0 even? Well, if we count down by 2's, we start out at 8, 6, 4, 2. These are all evens, right? 0. 0 is also even. It turns out that an even number, the definition of an even number, is one that can be written as 2 times any integer. In other words, it's divisible by 2 evenly. That is the definition of an even number. So 0 is even. Okay? So if you just have a number like 2 or 7, that is actually an even exponent term. So it turns out that all just basic numbers are also even functions. So if I have, let me clear this, y equals -1. That is even. That is exactly the same as if y equals x squared. Okay? Now, the next question is what happens if I start combining things? What about if I do y is equal to x squared minus 1? I've got an even term, another even term. If I combine them like this, is it still even? Well, let's head back to our graph and see what it looks like. So now let's enter in y, a combination y equals x squared minus 1. What do you know? It's still symmetrical. It turns out that any combination you can think of, as long as every term, every single term is even, the function itself is still even, and it has that symmetry. So y equals 7x to the 4th minus 3x squared plus 2. And what do you know? It's still symmetrical across the y-axis. The main thing is every term is even, every single term. We have an exponent of to the 4th here, to the 2nd here, and to the 0 implied here. Every one of those is even, therefore the function itself is even. So that's kind of cool. That is actually very, very cool. We can build up a polynomial with all the terms even and still have an even function at the very end. Alrighty, so now let's go back to the blackboard. Okay, so we've talked about even powers of x. What if I had odd powers? So what if I did f of x is equal to x? And since there's no exponent written here, it's an understood 1. Okay? So if f of x is x to the just plain x, then what would f of 1 give me? Well, that would just be 1, right? F of 2 would be 2. F of 3 would be 3. And f of 4 would just be 4. Okay, now what about f of -1? Well, that would be -1 to the first power, which is still just, I'll even write that out, that's just -1. And the same thing for -2. That's just going to be -2. F of -3 is going to be -3, and f of -4 is going to be -4. Okay? So, this one is a little bit different because if I take and plug a negative sign in, I get the negative of a positive signed input. So to write that, if I plug in a negative value for my x, I get the negative of the answer when I plug in a positive value. I plug a negative 1 in, I get negative 1. I plug negative 2 in, I get negative 2. And this right here, so forth and so on, this is the definition of an odd function. Okay, so if I plug a negative, the opposite sign in, I get the opposite of the original sign. That's it. That's what defines an odd function. So what does this look like? Well, before we get to that, let's go a little bit deeper and see what I would do. I want to prove one thing. Make sure that it's holding. So what if I had f of x equals x cubed? Well, let's see if this holds like the even functions did. Well, f of 1 would be 1 times 1 times 1, 1 cubed, which is 1. F of 2, I only do 2 because I know you don't want to do too many of these. 2 cubed, which is 2 times 2 times 2, which gives me 8. Now, what if I put a negative 1 in? Well, negative 1 would be negative 1 times, hold on, messed that up. Let me erase. Got ahead of myself. So let me try that again. That's going to be negative 1 cubed, which is negative 1 times negative 1 times negative 1, which is negative 1 times negative 1 is positive 1 times negative 1 is negative 1. F of negative 2 is going to be negative 2 cubed, which is going to be negative 2 times negative 2 times negative 2. Negative 2 times negative 2 is positive 4 times negative 2 is negative 8. And what do you know? It works. When I plug the negative in, the answer is the opposite sign of having the positive value plugged in. So it does hold that f of negative x is equal to negative f of x. Alrighty, so now that we've proven that x to the first and x cubed has this behavior, and both of these are odd exponents, we happen to know, based on that's the definition of an odd function, that's what should happen, but just going to prove it. Now let's head over to the graphic and see what these things look like. Alrighty, let me clear this. Okay, so here we are in Desmos again. Let's try this out. Let's see. X to the first. Okay, not a big shock because that's just y equals x, which that's what we would expect. It intersects the graph at y equals 0 and has a slope of 1. But what about x cubed? So x cubed, interesting. X to the 5th, x to the 7th. Now, I can tell that there's symmetry here, but what kind of symmetry? Well, the symmetry for odd functions is kind of unusual. It's as if you took everything that's to the right of the y-axis and then rotated it 180 degrees. That's the way that you can kind of think about odd functions. They have rotational symmetry around the origin of 180 degrees. You could also think, if you wanted to, that if I had a mirror on the y-axis, flipped it once, and then put another mirror on the x-axis, flipped it again, I'd have that symmetry. So you can even think of the symmetry of an odd function as either rotating around the origin, or it flips twice, once in the y and once in the x. And that'll hold. Okay? So with all of the symmetry that we had with the even functions, it should probably hold that the exact same thing should hold for the odd functions. And we can test that 2x to the 3rd. Well, what do you know? Let me turn these off so that I can see what I'm doing. Yep, still has symmetry. Doesn't matter that there's a number in front of it. Negative 8x to the 5th. Yep, still has rotational symmetry, spinning around 180 degrees each time. Alrighty. Now what if I added odd terms together? Well, 2x cubed minus x. What do you know? Perfect symmetry. So it holds for even functions as well. If you have every term, or for odd functions as well, if you have every term odd as an odd exponent for the variable, the function itself is odd, and you have the symmetry, that rotational symmetry around the origin. Okay? So, with that said, what will happen if I add odd and even terms together? Will I still have symmetry? Well, easiest way I can think of that is doing something like x squared plus x. Does that have symmetry anymore? No. The symmetry is broken. You could imagine that there's a line here and that's kind of symmetrical across that, but it varies for every single one of them. 3x to the 4th minus 2x. Yeah, good luck getting that one symmetrical. That one has absolutely no symmetry that I can see. So it turns out when you have even terms and odd terms in a function, you lose the symmetry completely. So we say that these functions that combine even and odd terms do not have even symmetry nor odd symmetry. They have neither. So let me go back to the blackboard. So an even function has all of the terms even. So x to the 4th plus x squared minus 3. And remember, the reason that just a plain number is still an even term is because it has an x to the 0 that's hidden behind it. So all the terms are, all the exponents are even. It's an even function, and that doesn't it doesn't matter if I have an odd coefficient in front of it. 3x to the 4th plus 5x squared minus 7. That is still an even function because every one of the variables has an even exponent, 4, 2, and 0. Okay? Odd. Well, same thing with an odd. X to the 5th minus x cubed plus x. That x by itself has an exponent of 1, and so every term is odd, so the whole function is odd. That includes if I have even coefficients in front of it, 6x to the 5th minus 2x cubed plus 4x. Every exponent, which is all you care about, is odd. Therefore, this function is odd. The two types of symmetry, this function will be reflected across the y-axis. This function will be rotated 180 degrees. So there's the origin. It rotates 180 degrees and then repeats. So now, neither. You have neither odd nor even functions when you have a mix of terms. So x squared plus x. That's an even term. That's an odd term because there's a 1 up above. Once I get them together, it's neither an even function nor an odd function. Symmetry is broken. It doesn't matter if I have something like 6x to the 4th plus 4x plus 2. I have an x to the 4th. I have an x to the 0 here. And then I have an x to the 1st here. The numbers in front of the variables do not matter. What matters is just the exponents. And so since I've got even, odd, this is still neither. Okay? That's it. That is all there is to even and odd functions. So let me give you some homework that you can work on. Clear this. Alrighty. So let's do the following for homework. So this is your homework. And by the way, I'm trying to write this all out because I know that not everyone has a book, and I don't want you to have to buy a book at this point in the semester. So here we go. Let's say that for number 1, we have if f of x is equal to x minus 4, and f of 3 would be what? F of negative 2 would be what? Just tell me what that is. For the second one, let's say I have f of x is equal to 3x plus 1. What would f of 1 be? And f of negative 2. Okay. Number 3, let's say that I have f of x is equal to x squared minus 4. What is f at 0? I do not have to do that. And what is f of 3? And finally, for number 4, classify each function as even, odd, or neither. And I'll try to write that. I don't know if I can write it. Yes, or neither. Okay, so first one is going to be, we'll do A is x squared plus 2. B is going to be x cubed plus 5x squared. C is going to be 2x cubed minus 7x. And D is going to be 9x to the 4th plus 3. And let's go ahead and star 2, 3, and 4. Those are the ones that will be for grade at the beginning of the next lecture. Alrighty. Hope you enjoyed it, and I will see you next video. Take care.